Okay, you should be seeing my page here. So quiz 14 is a series of reactions, all of which were on that chapter 8 review. So we have to kind of figure out how to analyze them. So in the first one, the first thing to notice is we've got a carbonyl group with 2 carbons on either side. So our starting material is a ketone, and we have an organometallic reagent. So that CH3MgBr is going to act as if it is a negatively charged carbon. This bond between the carbon and the magnesium is the nucleophile. It's going to attack the carbonyl group, and what it's going to do is break the pi bond and push a pair of electrons out onto oxygen. It's actually donating that pair of electrons into the lowest unoccupied molecular orbital, and the lowest unoccupied molecular orbital on that ketone is the pi star orbital, the anti-bonding pi orbital. So that's why the pi bond is the one that breaks. So at the end of step 1, we will have formed that new carbon-carbon bond. Right, so now a CH3 group here from the methyl magnesium bromide, and we'll have an alkoxide ion. And then this proton transfer step is simply the aqueous acid donating a hydrogen, liberating water, and forming the tertiary alcohol. So that's an example of a ketone being converted into a tertiary alcohol with an organometallic reagent. That's one of the types of reaction. Here you'll notice that we're starting with 3-pentanol, and we're ending with 3-pentanone. So we've got the same number of carbons. There are no carbon-carbon bond forming reactions involved in this reaction. All we're doing is removing 2 hydrogens, one from the oxygen and one from the adjacent carbon, to form a ketone. That's an oxidation. And since it's a secondary alcohol going to a ketone, it makes absolutely no difference which oxidizing agent you use. You can either use this one or this one, right? These are the 2 different oxidizing agents. So potassium dichromate in aqueous acid would be one way to do that, but you could also use this. This is PCC, by the way. Pyridinium chlorochromate. There's the pyridinium, there's the chloro part, and there's the chromate, CrO3. So that's an oxidation reaction converting a secondary alcohol to a ketone. Here you'll notice we start with a benzene. This is an organometallic reagent, right? So there's a nucleophilic bond here. And we're making a new carbon-carbon bond. The product is a secondary alcohol, and when we make a new carbon-carbon bond using an organometallic reagent to form a secondary alcohol, the starting material must have been an aldehyde. And we need that aldehyde to have 2 carbons in it, so the starting material must have been acetaldehyde or ethanal, and we would have done that in some inert solvent, and then just as we did in the top reaction, we would need an aqueous acid workup to provide the proton that's there on the oxygen. So this hydrogen here is the one from the aldehyde, right? And we made that new carbon-carbon bond. So that's another organometallic reagent. There are more carbons in the product than there were in the starting material. Pyridinium chlorochromate takes a primary alcohol and makes it into an aldehyde. We're not going to change the number of carbons. The cyclohexane ring is unaffected. We've got 1 carbon out here, so we're going to oxidize that alcohol up, primary alcohol, to an aldehyde with pyridinium chlorochromate. Here the thing to notice is the alcohol is formed with retention of stereochemistry. It's a substitution reaction. And we're not changing the number of carbons, we're not adding hydrogen, right? There's a hydrogen here in the starting material, there's a hydrogen here in the product. So what we need to do is convert a chloride to an alcohol with retention of stereochemistry, That's the Finkelstein reaction to start with, Ki in acetone. Right, that'll go with an inversion, and it will give you an intermediate that has the iodide back. So now you have the iodide back, and you want to convert this secondary iodide to a secondary alcohol, but you can't do that with hydroxide, because with hydroxide you would get elimination. So the second step is to use potassium acetate in a polar aprotic solvent like DMF or DMSO, and then the third step is the saponification step with KOH and water. The other intermediate after this second step with the acetate looks like this, where we have the acetate intermediate, and then we're cleaving this carbon-oxygen bond to form the hydroxide. So that's that three-step process. Ki and acetone to invert the stereochemistry once, potassium acetate in a polar aprotic solvent to invert it again, put it back where it was, and then saponification at the end. This is a reduction. We've added 2 hydrogens, right, and not changing the number of carbons. You can use either of the reducing agents. You can either use lithium aluminum hydride, which was on the last problem, or you can use sodium borohydride. It makes no difference. So I'll just say sodium borohydride and ethanol. That's one of the possible reducing agents, right, the borohydride ion. Here we have a primary alcohol, and we're treating it with an oxidizing agent. But we're in aqueous acid. And when you are in aqueous acid, you don't go just to the aldehyde, you go all the way up to the carboxylic acid. So we're going to convert that CH2 group to a CO and end up with the carboxylic acid 2-methyl propanoic acid. And then the last question on the quiz is a reduction. Lithium aluminum hydride is a reducing agent, hydride reducing agent. So that's going to add an H minus. So this nucleophilic pair of electrons is going to attack and break the pi bond. Pretty much the same donation into the pi star orbital that we saw in the first reaction, but now with this aluminum hydrogen bond as the nucleophile. That will form an alkoxide ion, just as we did before. And since this is an aldehyde, we expect the product to be a primary alcohol rather than a secondary alcohol. And then this is going to get protonated in the second step by your aqueous acid. You didn't need to show the mechanism, just to generate the primary alcohol. So benzaldehyde becomes benzyl alcohol. This phenyl ring next to a CH2 group is referred to as a benzyl group. It actually has the abbreviation BN if you wanted to, so you could have just have written this as BNOH if you knew that code. So that's the quiz.